We're going to be writing code here in what's called a circular array queue. But first, let's look at a picture. So here's my picture of a circular array queue. Rather than using a linked list, we're now going to use an array. So in this example, we have a capacity for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements. So we can fit 10 elements in our queue. We're going to simply keep track of, this is an array now, so these are all indices. We're going to keep track of where is the head of the queue, meaning the next element we're going to remove to play your video, listen to your music, play your video game. And where is the tail of the queue, meaning where will we add a new element coming from the server that's streaming your video, music, video game. Okay? So head refers to here's the element that we're going to remove next. Tail is here's where we're going to add the next element. So between head and just before tail here, these 5 darker shaded elements, this is all like valid data. Right now, we're not using the rest of this array. These 3 elements we're not using, these 2 elements we're not using. Okay? And so every time we get more data from the server, we add that element here and we move tail to the next index. And here's the cool thing. What happens when we add data here and tail is already at the next index? It wraps around back to index 0. And we keep adding it again. And same thing with head. What happens after we remove this element? Head moves to here. What happens after we remove this element? Head moves to here. What happens after we remove this element? Head wraps back around to 0. And we keep going. So you can kind of see the head and the tail chasing each other through the array as it wraps around. Right? There are potential problems here. Okay, this isn't like a perfect solution. And to be clear, this is exactly how your video streaming, music streaming, data acquisition system is implemented, is with a circular array as a queue. The problem we can run into, though, is what happens if the server is slow in getting us data. We're slow to get the frames of the video. We're slow to get the music. We're slow to get the video game information. What can happen is the head can catch the tail. And when the head catches the tail, we call that like an underrun error, a buffer underrun error. The head caught the tail. We ran out of data. And now guess what? Your video is going to pause or your music's going to pause, and that's a problem. The other thing that can happen is if we're not pulling elements off the queue quickly enough, the tail can catch the head. And we call that a buffer overflow error. We've gotten more data than we've processed. Okay. That's usually not too much of a problem with like your music and videos and video games, but it can be if you're doing like serious like scientific computing with the data you're acquiring in your lab, and you can't process the data fast enough, and so you get that buffer overflow error. Yeah, you could think of that like that gray bar is like a visual indicator of like how full your circular array is. Yeah, yeah, and there's no point in streaming more data yet. Yeah. All right, let's see what this looks like from a code perspective. We're going to see lots of familiar aspects in here. We're going to need a few instance variables. I said we were going to use an array to store our elements. So we're going to have an array of objects. Again, we're not going to write this as a generic. Let's add some other things that we need. So based on that diagram, we need to keep track of the index of the head of the queue. So we'll use an int for that, and we'll call it head. We need to keep track of where the tail of the queue is, the index for that, which we'll call tail. And we need to keep track of the current size. This one's a little bit more subtle, but if we don't keep track of the current size, meaning how many our elements are in a queue, a completely full array looks exactly the same as a completely empty one. right? So we need some additional data so we can distinguish those two cases. All right. Again, we have our Java doc. We're just going to like fill in the methods. Constructs an empty queue. So this is our constructor. So public circular array queue. We're going to initialize all of our instance variables that we have. So let's do each of those. This dot elements equals, so it's an array, so we have to actually make a new array. Elements, plural, equals new object array. And let's, by default, let's have 5 elements in our queue. This dot head equals 0, because the next time we remove something, it's going to be from index 0. This dot tail equals 0, because the next time we add something, it's going to be at index 0. But this is why current size is important. We need to set the current size to 0 so we know there are no elements in this list. If we try to remove something right away, we need to throw an exception. All right, everything is initialized. Let's implement some other method. Checks whether this queue is empty. That's describing our empty method. So public Boolean empty. This is why we have the current size instance variable. So we'll simply return this dot current size equals 0. If the size is 0, our queue is empty. All right, adds an element to the tail of the queue. That's describing our add method, which takes one parameter of type object, which is the element to add. What we need to do is to update all of these instance variables to reflect the fact that we have added a new element, or almost all the instance variables. Adding an element doesn't change the head, but adding an element definitely changes the tail and the current size. So let's go through each of those. We'll do this dot current size plus plus. We've added one more element. Let's actually put the element in the array. So this dot elements sub this dot tail, because tail stores the index where we're next going to add our element. That equals element. Once we've used tail, we can then increment it. But we have to check for the case of what if tail was at the very end and we want it to wrap around the beginning. Yes, this is where we can definitely use our modulo operator. This is a great use of mod. So we can say this dot tail. I usually write it like this. I use mod equals this dot elements dot length. Okay. So what mod equals does is it says this dot tail equals this dot tail mod this dot elements dot length. So our length is what? 5. So if tail equals 5, 5 mod 5 is 0. It assigns 0 to tail. If tail equals 3, 3 mod 5 is 3. It assigns 3 to tail. What we need to also account for here in add is the possibility of a buffer overflow error, meaning there is no room in our queue. There are a couple different ways we could handle this. In very high performance applications, we can't afford to allocate memory. And so therefore we have to just stop. So we would like throw an exception and say, we got a buffer overflow. You got to adjust whatever you're doing to make this work better. And that's appropriate in some applications, like very high performance data acquisition for like your research in your lab. For a video, we don't really want to like crash YouTube, right? If we're going to have a buffer overflow error, we're just going to make our buffer bigger, right? In the case of YouTube, like, no, it probably would just pause and there'd be more going on, but we're not going to worry about that. So we're going to add just another call here at the beginning of add that says this dot grow if necessary. And that's a method that we're going to uncomment in a moment and just look at the code a little bit later. So the approach we're taking for our circular queue is like, hey, if we're out of room, okay, we'll take the performance hit of making the array bigger and dealing with that, and then we'll add our element. So different trade-offs for different applications. All right, let's look at remove. Public object remove removes our element. We got to still maybe throw an exception here. So if we get a buffer underrun, we have to do something. That's a problem. So if this dot empty, if it's empty, just like we've been doing, we're going to throw our new no such element exception. Otherwise, we'll just update our instance variables. So we'll say this dot current size minus minus one fewer element. We need to get that element. So we do that by saying this dot elements sub this dot head. The value of head is the index of the next element to remove. We now need to change this dot head. We could write very similar code as we did here, where we increment head and then we do this mod thing. Another way to write this, which does it kind of all in one line, which you'll see probably more commonly, is something like this. This dot head equals this dot head plus one mod this dot elements dot length. So we're doing the increment here. Oops. Then applying the mod operator based on the length. So this is like kind of your super common wraparound statement. Add one, mod it, assign it back. And we return the element. And we could do other behaviors here too. So here we chose to throw an exception, which will kind of bring this all to a halt. We could have instead chosen to pause, like, oh, they want more data. There is no more data. We will wait for it. And we just kind of sit there and wait. That's that lag you might get in YouTube until the data is available, and then this method will return. So different ways to implement this for different situations. All right, let's uncomment grow if necessary. So this is, I wrote this for us. It's a good algorithm. This is very similar to what we were just discussing in terms of what happens when our array list is full. Well, if our array is full, we make a new one that's twice as big as the old one. We then go through and copy all the elements from the old one into the new one. Update our instance variable, reset head to 0, reset tail to like the current size. The way we copy this is a little bit sophisticated. So head is somewhere in the old array, okay? We're going to copy whatever element is at the head to index 0 of the new array. So basically when all is said and done, head will be at index 0 and tail will be at, later on. And so this code does that. Deals with the wraparound and everything else as we copy all of the elements from the old to the new. So somewhat sophisticated algorithm right here with the for loop, but a good way to do it. Question? To do what? I'm sorry, say.
It's like said we have like a grow if necessary.
Yeah.
You also have like a remove if
Like there's a lot of free space in it.
Yeah.
We certainly could. Like we could then do the opposite of this, right? Often we don't really worry about it. We figure like if it needs to get bigger, it's probably going to stay at that size or get even larger still. But we certainly could. Yeah, we could certainly have something that kind of cleans it up if it gets too large. Again, it all really depends upon the application and what the needs are for that algorithm. If we switch over here to Q demo, that demo code is already written for us. We just have to uncomment it. And what this demo code is going to do is to create a circular array queue, add Tom, add Diana, add Harry, call remove, which gets rid of Tom, add Romeo, call remove, which gets rid of Diana, add Juliet, add Maria, and then like remove everything at once and hopefully the order it expects. 1, 2, 3, 2, 3, 2, 4, yeah. So we can run this and make sure it works well. Yay. This isn't a great test because we're not actually causing the queue to have to grow. So we could add a couple more elements here. And this tests that it wraps around, but it doesn't test that it grows. So we could make this better.